Why do astronomers think we'll never reach the universe's boundary? Perhaps after watching this video, you'll have the answer. This is a real photo of the Milky Way. In the photo, besides the magnificent Milky Way, you can also see distant star clusters and red nebulae. However, most of the lower area is pitch black, as if there's nothing there. Don't worry. The miracle is right here. As we gradually zoom in on this dark area, we'll discover that the originally void space is actually filled with countless light points, just like the starry sky we see at night. As we continue to zoom in, we'll see this magical scene between the starlight. There are countless large and small bright spots, and each bright spot is actually a massive galaxy. The sheer number is unimaginable. What exactly is the universe hiding from us? When night falls and we point the telescope at the starry sky, humanity embarks on a journey across time and space. What is the true meaning of astronomical observation? It's never just about stargazing, or rather, it's humanity's only way to go back in time, because human history is only a few million years old, just a fleeting moment in the river of the universe. With so little experience, how can we understand the universe's past? Fortunately, the universe considered this in its design. It gave us a very user-friendly setting. The speed of light is finite. The sun we see is its appearance 8 minutes ago. Every beam of starlight in the night sky is actually a time capsule from the distant past. In other words, as long as the universe is large enough and we look far enough, we can definitely see the universe at its birth. We can return to that moment of primordial chaos. This ability to look back allows humanity to break free from the limits of our lifespan and civilization's length, to touch the universe's origins and evolution firsthand, observing the dance of stars across billions of years, understanding the past, predicting the future. It sounds unbelievable, but after the Hubble Space Telescope launched, it slowly became reality. Hello, I'm Sun Tzu. Starting from this video, I'll use 3 episodes of premium content to deeply explore with you the most shocking series in astronomical history, and the one with the longest time span, Hubble Deep Field. Before the main content begins, we need to understand what deep field really means. In my view, deep has 2 layers. The first is extreme spatial focus. It must be far enough away and not greedy for quantity. It needs to target a narrow area in the sky that appears empty. The second layer of deep is a temporal span of billions of years. Its essence is gazing at the distant past, because light propagation takes time. By the time this light reaches Earth, it may have traveled tens or even hundreds of billions of years, so the celestial bodies we see might be in their infancy, and field is easier to understand. It refers to a specific region in astronomical observation, that is, the patch of cosmic space the telescope lens points at. But this field isn't chosen randomly. It must meet 2 conditions. First, it must be clean enough to avoid interference from bright stars and nebulae in the Milky Way, ideally an area that looks pitch black to the naked eye. Second, it must have representativeness. A small area can reflect the general state of the universe. So, deep field combined is a profound gaze at the universe in an extremely small spatial range and across billions of years. Now that we understand the meaning of deep field, we need an opportunity to realize it. On April 24, 1990, the Hubble Space Telescope was successfully launched, but to everyone's surprise, the first images transmitted back were blurry, impossible to make out what they showed. A multi-billion-dollar project that wasn't even as good as ground-based telescopes. After repeated troubleshooting, the team confirmed the main mirror was miscalibrated during manufacturing, making it 2 microns thicker than designed, preventing light from focusing. In short, at that time, Hubble was essentially nearsighted. Transcript truncated in original. Continuing from provided text. Beneficial for precise positioning during Hubble's long exposures, while also meeting the deep field's representativeness requirement. During Christmas 1995, Williams led the team in observing this sky region with Hubble for 10 days, conducting 342 exposures, each about 30 minutes long, ultimately yielding the first Hubble Deep Field image in this area, which is 1/26 millionth of the entire sky, about the size of a coin held at arm's length. At least 1,500 galaxies emerged like stars. After this, astronomers realized the universe is filled with galaxies everywhere. Those areas that appear black from Earth actually hide tens of thousands of galaxies inside. The Hubble Deep Field completely changed humanity's understanding of the number and distribution of galaxies in the universe. You might wonder why the top right corner of this deep field image is missing a piece, and it's missing in a very flat way, which looks strange, but if you've seen more Hubble photos, you'll notice many are missing a piece. This is actually the shape of Hubble's camera itself. More precisely, it's the shape of its light-sensitive CCD element called WFPC2, which translates to Wide Field and Planetary Camera 2. This name sounds a bit awkward. Why not just call it Wide Field Planetary Camera? Is this camera a combination? Well, it really is. WFPC2 has 4 identical CCD detectors, each 800 by 800 pixels, 3 arranged in an L shape forming Hubble's wide field camera, and the remaining one is the planetary camera, equipped with a narrower focal length CCD for more detailed views in a smaller field of view. Usually images from the wide field and planetary cameras are combined, generating WFPC2's characteristic stepped image, but what we see is a color-processed version. Astronomers receive raw scientific image packages with richer details and data. Note that these two camera groups can't shoot directly. Special filters are needed for images, so WFPC2 has a mechanical structure, a rotating wheel that switches different optical filters, with 48 filters in total, including narrowband filters for specific spectral lines and broadband filters for studying stars and galaxy spectra for shooting the Hubble Deep Field. It's about throughput, that is, the ratio of light that can pass through. After all, these galaxies are extremely distant from us. The light they emit has become very faint by the time it reaches Earth, so astronomers must consider the spectral range it covers and ensure the filter's passbands don't overlap. After careful study, the imaging team selected 4 filters for the Hubble Deep Field, namely 300 nanometers near ultraviolet, 450 nanometers blue light, 606 nanometers red light, and 814 nanometers near-infrared. Note that Hubble's detectors have very low quantum efficiency for 300 nanometers wavelength light. Observations at this wavelength have noise, mainly from CCD noise rather than space noise, so this wavelength is only used when background noise affects other bands. Efficiency from December 18 to 28, 1995. Over 10 days, Hubble orbited Earth 150 times, capturing 342 photos in the selected sky region, each an independent exposure to reduce cosmic ray damage to each image, because cosmic rays create streaks when hitting the CCD, and precisely because of independent exposures. After all photos were taken, extensive processing and mosaicing was needed. This process not only removes cosmic rays and scattered light interference, but also eliminates space debris and artificial satellites from the raw images one by one. Once all 342 photos are denoised, they can be mosaicked together. Thus, we truly obtained humanity's first deep field photo, Hubble Deep Field.